Hi everyone, this is Miloš. Welcome back to my channel. I'm very excited to announce that Google Open Buildings Dataset has got a new family member, which now includes building height and building presence for all those cities in South America, Africa, and South and Southeast Asia. So in today's tutorial, I will show you how you can fetch the building height and presence data, how you can filter this data, and then how you can merge this with the building polygons for a specific part of Mumbai, and then create some very crisp 2D and 3D maps using ggplot2 and rayshader in R. Alright, our first step in today's tutorial will be to install and then load the packages we need. To do that, the easiest way would be to first of all install, unless you already have package pacman. Then using package pacman, we can actually install and load the remaining packages. And the first package we need to install, and the most important in today's tutorial, is RGEE package, which is an R wrapper for Google Earth Engine, which is going to help us get the Google Open Building data into R. The second one that is also necessary is Terra package, which is going to help us work with raster data. And in this tutorial, raster data will be in the form of building presence and a building height dataset. Then, of course, we will also load Google Open Buildings in the polygon form and use those later on to create 3D maps. Now, in order for us actually to calculate the average height for those buildings and for every polygon building, we will also need to do zonal statistics. And one of the best packages for zonal statistics is exact extract R. Now you can also do that in Terra, but exact extract R was built on top of C++, so it's extremely fast. Then we will also want to visualize these results eventually, so we can use ggplot2 from Tidyverse, and also for data wrangling we can use dplyr, which also comes as a part of this umbrella package. Then, of course, for creating 3D maps, we will be using rayshader. And finally, we will also enrich our maps with OpenStreetMaps data on roads. So that's why we're using OSM data package for that purpose. So as I mentioned at the beginning, we will be connecting to Google Earth Engine using the R wrapper through RGE package. And if you want to set this one up, I suggest that you go ahead and check one of the previous tutorials where I show you step by step how you can do so. In today's tutorial, we're simply going to continue from the part where we already authenticate ourselves and then initialize a connection to Google Earth Engine in R. Okay, once you have your Google Earth Engine account set up, once you have also RGE package set up, Python installed, we can go ahead and use RGE to first of all authenticate ourselves in Google Earth Engine. Right, so once you do this, it's going to open your browser of choice, and then it's going to ask you to authenticate yourself. So basically you need to authenticate yourself and then generate token. So you can click here on the generate token blue button, and this will take you then to another page where you need to choose your Google accounts. And after that, click on continue to continue this process. Select all of the options here to enable, of course, the Earth Engine client, and then click on continue. And once this is done, you will then see on this new page, you will see your authorization code. So you just need to click on this thing to copy it next to it. And then we'll head back to R, where we will use this token then to initialize our connection to Google Earth Engine, and we can then work in R. Okay, so you will go back then to the terminal here where you're writing your code, and you will have this message to that the authorization will generate the code and that you should paste it here. So this is where you should enter your verification code, meaning paste it. And once you do that, you just need to click on enter, and you should be able to get this message that your authorization code was successfully now saved. After you successfully authenticate it, the one remaining step is to initialize your connection. So you need to actually write here EE. By the way, this EE means Earth Engine, and almost everything of these commands within RGE actually start with this. So that's something to also remember. Then you need to write here your username. In my case, this is simply my email that I previously used to authenticate myself and also get that token. So I'm just going to write that one here. And then after that, what is also very important is that you also enable that any actually files that you download are going to go to your Google Drive. So that's also important that you have your Google Drive, which comes, of course, for everyone who has Gmail, it comes as a part of it. And then once you run that chunk, you should be able to see the following messages. And the most important ones is that you successfully initialize your Google Earth engine, that your Google Drive credentials were found. And of course, there is also a Python path, which is very important for us because R will communicate actually with Python on the Google Earth engine side. In today's tutorial, we're traveling to Mumbai and we will be making building heights map of Mumbai, or actually to be more precise, of a specific commercial district, this one here. So I'll be just getting the coordinates for this one. And if you're familiar with Google Maps, it's very easy. You can get it for also other areas. You just need to click on the area of your interest. And then in the link, you will see also the latitude followed by longitude. All right, back in R, I just wrote down the latitudes coordinates and the longitude coordinates as well. And now we're actually going to create a 1 kilometer buffer around this point so that we have actually within that buffer eventually a certain number of buildings. So what we're going to first do here, we're going to create an object called, let's say, sense. And then using these coordinates, we're going to first of all define here a data frame that has two elements to it. So one is going to be latitude, denoted by lat, and the other one is going to be longitude, denoted by this object lon. And once we do that, we will turn this into an ASAP object. And to do that, we need to define this, that we are here having actually coordinates. Coordinates having two elements, so it's important that this starts with longitude, so lon first, and followed by latitude. And it's also important that you define here also the coordinates reference system, or CRS. So for the CRS, we simply want this to be EPSG colon 4326. So that's the first thing. This is going to create centroids, again, in the SF format. The second thing we want to do is essentially create a circle here, or like this buffer. And for creating a buffer, we can use a function stBuffer from the SF package. Now within this one, what we are going to do is we're going to pass this sense object, so the centroids, and then we're going to calculate here a distance. So as we said, we want to have a 1 kilometer buffer around this point. So I'm going to set here, I'm going to use units, and then I'm going to set units, and I'm going to say I want 1 kilometer, just like this. And then the final thing you want to do here is, again, make sure that you set here, that you set the coordinates reference system. So set ST, set CRS will actually do that for you. But again, you need to provide here this same coordinates reference system that we used over here. Now for our work with Google Earth Engine, it's very important that we define the bounds for which we want to have the data, because the data is itself huge. The dataset open building is also huge. So what we're going to do here is use that buffer that we previously created, so this one, which we call circle, and then based on that, we're going to create a bounding box around it. So I'm going to call this object CityBbox, and then I'm going to use from SF package something which is called stBbox function, which is going to make this bounding box for us. So I'm just going to pass here a circle, and then once you actually run this, and once you inspect, you will get here a small object, small table with the values for your bounding box. So there's going to be your minimum longitude and maximum longitude values, as well your minimum latitude and maximum latitude values. All right, so now knowing this, what we want to do next is we want to create a rectangle that we can pass to Google Earth Engine, and then based on that rectangle, we're going to get the data only for that rectangle. And that rectangle is exactly going to be this bounding box here. Now, how do we do that? We're going to define something which is called city bounds. And then before we actually do that, I want to actually extract here those minimum longitude and maximum longitude and minimum and maximum latitude values. So I'm going to extract, first of all, xmin, and I'm going to use this CityBbox that we just created. And then I'm going to fetch using these double brackets, and I'm going to put inside exactly what I need. So I need this x min because this is the minimum longitude value. And then I'm going to do the same thing for the rest. So I'm going to also have here the maximum longitude value as well. And then I'm just going to copy these two and change x with y to have also the latitude values, all right? So once we have this, then we can move on and create these city bounds. So the city bounds, again, this is an object rectangle. It's an Earth Engine object that we can then pass to our query for Earth Engine so it understands that we simply need the data for that bound. So here's how we do that. So first of all, we start with this EE, so that's a standard way of communicating with Earth Engine. And then the second one is we're going to say that we're going to create a geometry here. And the type of geometry that we're going to create is a rectangle, because rectangle is essentially this bounding box. Then within this one, we need a list of 4 elements. So one is west. West is, of course, your minimum longitude value, because it starts from the west and goes to the east when you are measuring longitude. So this one is going to be x min. Then we have south. South is your minimum latitude value. So that's going to be just y min. Then we have east. East is the maximum longitude value. And then we have north, which is the maximum latitude value. Okay, so we now have these 4 things. And then what is very important is that you define that this is actually a polygon. So to do that, you need to specify here that geodetic equals true. And once you do that, the very last step, but also very important, that you need to let know this function here about your coordinates reference system. And again, we're going to be using the same one that we used also in the previous steps, which is going to be EPSG 4326. Okay, so our next step is going to be to connect to Google Open Buildings 2.5D temporal dataset. So this is the dataset that has information about building presence and building height. And this website is at sites.research.google/gr/open-buildings/temporal. So don't worry about it. I'm going to provide this in the description box below this video. But for now, what we're going to do is we're going to go through this dataset so you see what is the coverage. Well, first of all, what is very important about this dataset is that this is a temporal one, and it has information, as you can see, about the so-called global south, essentially Central and South America, Africa, and then the South Asia, Southeast Asia as well. So this is the coverage in general. You can see also on the map if you go here, then you can see, some ads about, what is the use of this data, how we can also explore it if you slide down. And for us, the most important thing is how do we download this data? You can also, check out a bit more about this data set and frequently asked questions. But for now, I think what is very important is where do we download this data? Before we jump into that, however, I would quickly revisit this frequently asked questions where you can find how this, data set was built, what is its resolution, how do I interpret different values. So one thing to understand about this one, this data set has confidence values. It means that there is a certain percentage of confidence values about the model that gave us prediction whether there is a building or not. And this is something very important because the way we're going to use the building height data here, it's going to depend on what is the confidence of the building, of the model that the building exists there. So when you actually go to this part, and there is a question which says, how should I use the building height raster? And if I expand on this question, it's going to tell you this, that you should be only used in conjunction with the building presence, meaning pixels with low confidence should be masked in the building height raster. So for us, what is important is not only to go to the download section and download height, we also need to download building presence, which has confidence levels, and which is going to then help us filter out those pixels for which the confidence level is very low. So knowing this, what we can do next is we can go ahead and go to the download page. So if you go actually here to this part, which says the dataset is composed of single Earth Engine image collection with 3 rasters, you can actually go ahead then and to the next paragraph, which mentions here image collection. So you can click then on this link image collection, and this is going to take you to the Earth engine here where the dataset is. You can see that the dataset is available from 2016 until 2023, and I'm going to show you how you can filter those. Whereas the most important thing is the link to this dataset. So this is actually the link, exactly the one that I highlighted. And once you highlighted this, please do copy this link, because we will then use it in R to fetch this data. Now, if you go actually down, you will also see more information about this, that, you know, there is also the building counts, there is building height data and building presence. Again, we'll be using building height and building presence. Building presence only for filtering, actually, again, those pixels in the building height, and then building height eventually we'll be using for creating 2D and 3D building height map for our area of interest. All right, we are back again in R, and over here I just pasted this link to the building height and presence dataset. And what I'm going to do next is put double quotation marks around it so that I declare it into string. But that is not all. In this part, we're going to connect to this open building data. And for that, we will first of all create an object, which I'm going to call Open Buildings Temporal. And then I'm going to provide actually a link to this one, so the name to this one. Now to connect, we need to again call this EE function. And then as you saw there, this object is called image collection. So I'm actually calling this function image collection so that Earth Engine knows that, you know, what it needs to use. And then after we have that, the next thing is I want to declare here that we don't need everything. We need only the data for the bounds. And the bounds, in our case, it is city bounds, which we also defined. So once you have this, and once you actually run this, nothing is going to happen. So what you need to do is you need to actually go and then print this data set. And to print the data sets, we again need to call here RGE, and there is a very convenient function which is called EEPrint. And then we simply need to pass this object that we created, Open Buildings Temporal, and then I'm just gonna open up the terminal and then just run this. And in a few seconds, you should be able to see the description of the data set that we want to fetch. So we haven't fetched it yet, but we will. So again, we successfully managed to do it. So you can see here, because of the name that is mentioned, the ID, you can see that it's a huge data collection, so 4.41 terabytes. It has a specific coordinates reference system here. All right. Then this is, of course, you can see also the size for specifically for the building count, so for specific bounds. And you can also see here the temporal resolution. So for example, for now it says here that there's only 2016 start and end, but you can definitely also fetch for 2023, which is also what we're gonna do next. All right, so once you have this information, we can go and proceed to the next part, which is about, of course, getting those raster files, those bands. So in this part, we will actually load the data into R. And to do that, we need actually to get two bands here. And you probably saw them in this Google Earth Engine interface. And those are building heights. So building heights. And the other one is building presence. Okay, why did I actually do this? Why did I define this? Well, that's because we will essentially need to pass to Google Earth Engine what we want from it. And some of these bands have, of course, this in the name, so it's going to be way easier to identify if you already have predefined names. Now, once you actually have this, we can go ahead and filter specifically those building bands that we need. So we're going to go ahead and then choose this Open Buildings Temporal dataset, and then we're going to have this this function which is called select, meaning we want specific things. And then we're going to pass here that we want these variable names. Then very important thing here is we want to convert this image collection into specific bands. All right, so then you can actually run everything here. And then the very last thing is to check, okay, let's print again using this EEPrint from RGE. And let's see actually what are the names of these building bands that we are now asking Google Earth Engine to connect us to. Now, if we inspect again that building bands object, what we are going to see here is band names. And you can see there's a bunch of them. You might be actually frightened that there are so many of them, 16 in total. But essentially what you will see here are two types. You will see building height and building presence as we want it. There is also one more thing, which is there is, for each of them, there is a file for 2016 to 2023 for each year. And one thing you will notice, every file starts like this, at least for this city, for this part of Mumbai. This is 3B underscore EPSG underscore 32643. So this is basically the coordinates reference system. And then it goes underscore and then year underscore month underscore day. Now, month and day is the same, but what changes here is the year. What I would like to do is actually get us the data for 2023. So essentially this string. And then I want to get data for 2023, both for the building presence and building height, because I want to filter building height based on building presence. So in the next step, what we're going to do, we're going to actually create exactly the names of the bands we want by gluing this part of the string with both building heights and building presence. So that part that I just showed you, so this is the part of the string. And I'm actually going to declare it as a string. And then I'm just going to call here, so I know what's going on. It's going to be string ID. And essentially it is. So this is a string ID for those raster files and for 2023. So we want the most recent data. Then the next thing, we're going to actually construct true band names. We're going to glue together, as I said before, the string ID. And then we're going to glue string ID with variable names that we previously declared. So actually then once you run this, and it's going to be of course successful if you did everything correctly, and then if you inspect the band names, you will see now these two band names. So this is for building height and the other one is for building presence, and both are actually for 2023. So now that we have these band names, we can go ahead and tell that we just want these building bands. So I'm actually going to call this not building bands because we already use this. I'm going to call it building data. And then I'm going to call building bands. And from then I'm going to select only these previously defined band names. All right. And once I do that, last important step is this is an image object that we're getting, so these two bands, and I'm going to clip it. And I'm going to clip it by those city bounds. All right. And we are finally ready to pass this query that we previously defined to Google Earth Engine and ask for this specific data. So I'm going to call this buildings raster, and then I'm going to use RGEE. And then from RGE, there is a very convenient function which is called EE as Rast. This is basically going to return you a spot raster file, which is in the format for the Terra package. But before you do that, you need to provide several things. So what is the name of the image? The name of the image or that queries is essentially the building data that we define. That's the first thing. The second thing is how your file is going to be called once it ends up in Google Drive. For example, we can call it, it's not for the entire Mumbai, but you know, why not? So we can just call it Mumbai buildings dot, and this is important, .tiff. So this is going to be a TIFF file. Now, in terms of the max pixels, what is very important is to understand over here in this building data, how many pixels it has so that we can set here the maximum. So actually, what we need to do next is we need to inspect beforehand this building data set. And again, as we did in previous steps, we're going to simply use here EE print from RGE, and then we're going to paste this building data here in the brackets. And then we're going to run this. And once we run this, we will definitely see what is the number of pixels for which we need to get the data. It's very important because if you don't provide the correct number of pixels, then the operation is going to abort. All right. So where do you check pixels? Because there is this number of pixels and there is this second one. So the one without asterisk, so the second one, this is what you should be looking at. And this is 16 million pixels. So you need to declare something which is either this number. So you can go, for example, click, and copy this, or you can define yourself if you want. So for example, I'm just going to go back here to our code. And then here for max pixels, I'm going to say, for example, 17 times 1e6. So 1e6 in R means 1 million. So 1 and then times 6 places. So that's 1 million. So essentially what this is going to mean is 17 million. Again, maybe this is too complicated. If it is, you can just copy and paste that number that I showed you and it's going to be fine. Then you also need to define here the region. And as we did before, we need to pass here city bounds. We did put here clip, but this is simply for getting information on the data. Now we are essentially going to load the data into R. And then the last step is I would like to get also this TIFF file through G Drive. If everything went right, you should be able to see here how much it took. So for me, it was 215 seconds. It's going to vary. It's going to be different for everyone. But the most important thing is that you here see that the state is completed and the image is now moved to Google Drive to local. At the same time, it also is there in our newly created object. So I'm also going to show you how you can save locally that file to your local drive. The data is also stored in this buildings raster object, which means that once you open this one, you will be able to see that this is essentially a spot raster file, as you can see here. And you can see the standard information about it, which includes dimensions, resolution, extent, of course, in this specific coordinate reference system. And you can see here that it has two layers, building site and building presence, just as we want it. Because this is a Terra raster file, what you can also do, you can save this file locally and then reuse it later, which is also pretty cool. So you can use Terra write raster function. So over here, you can simply then put that you want to save this building raster. Then you can provide the file name. So for example, for the file name, you can use essentially the same name. So this is just going to be locally saved. And then if you, for some reason, already have something under the same name, you can, for example, overwrite this file. And then once you actually save this locally, and it's going to save it pretty fast, you can also go ahead then and load it. And let's say we load it under the same name. And to load it, you can simply use then Terra Rust, and then you can pass this name here that you just used previously to save this raster file locally. So if you remember, we got a single raster file with two layers. Now what I would like to do next is to split this raster file into two raster files for building presence and for building height. Now to do that, what we essentially need to do is, first of all, we're going to check the names here. So we're going to check the names for this buildings raster object. And one thing you will notice is that it has two names. Now, the problem with the names is that it starts with a number here. And now if I split them into two raster files, then they're going to have this name which starts with a number, which is not that great. Because then every time you actually call this object, you will need to put here single quotation marks. Now, to prevent that, we can simply get rid of that first part with the number and everything else, and just leave building presence and building height there. So I'm gonna then create quickly new band names for those layers, and then what I'm gonna use is here this sub option. Sub allows you to get rid of the first part. Luckily, I already have defined the first part, so that is that string ID. Then I would, instead of that string ID, I would not like to leave anything, so I'm just gonna delete it. And then I'm going to replace this with the names of the buildings raster. So what I want to replace here is actually the building raster names. So then what I can do is run this. And once I run this, I just want to show you here in the terminal what I got. What are going to be the new band names? So the new band names are going to be building height and building presence. I mean, I could have also used simply those variable names that I defined. So that's also fine. I just wanted to show you how you can also do that. And then we're going to go ahead and change the names of this building raster. And we're just going to pass here new band names. All right, just like this. And then actually, if you check then again this building raster object, there will be here two objects, basically building height and building presence, just like we want it. But this is not all, because what we now want to do is we're going to create now two raster files out of this one raster file. So one for building presence, the other for building height. To do that, we need to create a for loop. And then over here, what I'm going to do is I'm going to say layers in names, and names of this building's raster file. So for those, I want to actually create here, I want to create a change. And then I'm going to actually open like this. And I'm going to say within these curly brackets, what I want to do. I want to assign here. So I want to assign that each layer in this building rasters becomes actually a separate raster file. So that means for every layer within this building rasters layer, I want it to become a separate raster file. So actually, if you then run this, this is going to create two objects then. And those objects are going to have the names building heights and the building presence. So exactly those variable names. So we can go, for example, and we can also inspect them. So for example, let's start with the building presence. Just type it like here and then run this. You can see here, this is now a separate raster file. And same goes, for example, for building height. You can also check that one out. It should give you also this information. So yeah, just below this one, there's also the building height, a separate raster file. So if you run TerraPlot, you should be able to see the plot like this. This is the building height data that goes for this specific extent from 0 to somewhere 95 meters. And then if you plot building presence, you should be able to see a bit more colorful one, because it also includes buildings with different confidence levels. And this is essentially what you see also on the legend on the other side. So the confidence level goes from 0 to 1. Essentially, those are the decimal values of percentages, which would be from 0 to 100%. In the next step, we're actually going to go and filter the building height based on these confidence values, where we will actually take a threshold for our exercise. And to filter heights by confidence levels, we're first going to define a confidence level. Now for this one, you can take anything you want, but I'm going to take 70% as a threshold here for confidence level. So everything that is equals to or is greater than 70% confidence level, I'm going to take that as a well enough measure of building presence. Then I'm going to create actually a mask raster. So this is going to be a raster file that is going to be based on this value of confidence level, which is equals to or greater than 0.7. So to do that, I need two functions from Terra. So the first one is if-else, which is essentially if-else. And the second one is Terra init function. Now I'm going to say the following thing. So I'm going to say that for building presence, run this function if the value of the building presence is equal to or greater than the confidence level that we previously defined. Okay, so if this is not the case, then I would like to declare this to be missing. So essentially, I don't have confidence that the building actually is there. Otherwise, please return the building presence value. So this is going to be our mask raster one. Okay, and then what we're going to do is we're going to create object called building height mask, and essentially we're going to mask our building height data. So we're going to mask building height data using this mask raster that we previously defined here. Now, once you plot this newly created raster, you will see there are a lot of flakes here. And these flakes are essentially all those pixels that we removed because they had a confidence level which is lower than 70%. So it would have even more flakes if we, for example, increase the confidence level, and vice versa. It would have fewer of these flakes if we, for example, decrease the confidence level. So we would essentially then allow more pixels to be considered as the building level. So having this in mind, we will now use this and in the next step get the actual building polygons, and for them we can then calculate this height data based on this raster file that was masked and filtered. All right, so we are back in Google Earth Engine Data Catalog, but this time we are looking for another data set that Google has released before the one on building presence and building heights, and it's called Open Buildings Polygons. Now it's at version 3. Don't worry, I will provide a link to this data set in the description box below, so you can then check it out. But for now, what is important for us is to actually understand this data set a bit. So this one is also derived from satellite imagery, and it has actually the same coverage. So it covers Central and Latin America, Africa, South and Southeast Asia. So that's perfect. The dataset is current, so that's 2023. So that is why it's important that we also got the building height and the building presence data for 2023. If you want to, find more information about this dataset, you can check the description over here. Or if you want to see how you can fetch it in Google Earth Engine, you can also check some snippets. But since we want to work in R with this data set, the next thing we want to do is head to this feature collection part. And inside of these brackets, we need to copy this path, because this is the path to the data set that we will then use in R to fetch it. Okay, we're back in R, and I just again pasted here the link to the data set. I turn it again into a string. So we're doing essentially a very similar thing that we did before. I'm going to call this one Open Buildings Poly. So to just indicate a different type, we're talking about polygons. And then over here, we're going to again call this EE function. But this time, as you probably noticed, when we were in Earth Engine, this is not anymore an image. So this is called a feature collection. Feature collection essentially are shapefiles. So we're just going to put this into the brackets, and then using this $, we're going to call again this filter bounds function, for which we're going to actually say to this data that we just are interested in information about this specific area. So this is the same what we did before. And then again, if you want to inspect this data, you can again use this EE print function that we used before, and you can simply pass here this open buildings poly as well. Now, why is this important? It's important because we need to also see how many features we need to load into R. And if it's too many, then we need to be sure that we know how many to pass. Very similar to the number of pixels that we did in the previous step. So then if you run this EE print on this Open Buildings Poly, you will be able to see some information about it. And one of them is that we're talking here about almost 5K features. So you can either copy this number, or we can just provide 5K as a number in the next code chunk. All right, so it's time to fetch also the building polygons, and we can save this into a new object. And then from RGE, we can use another very convenient function, which is called EE_as_SF. Essentially, this is going to save this object, so these polygons, as SF object, which is perfect for us. What we just need to do is we need to provide the name of this feature collection. So it's this one. And then the second thing we need to provide is what is the maximum number of features. So I think by default, it's 5K. So we are actually fine. But if we're not fine, we can just simply type here 5K. We are below 5K, so that is totally fine. So we fetch the data in a matter of a few seconds, much faster than the images, but that's because this is not a big data set. It has less than 5K features, but what is important here is that you can see there are also here confidence levels. So we could have maybe also used this one, to filter out the unnecessary ones. And then you should be able to see here as the last field also geometry, polygons, which tells you that buildings are essentially the polygons. The same way we filtered raster files based on the confidence levels, we can also use this, and we should use also on the building polygons. So let's actually go ahead and use the same object and simply subset the values based on those confidence levels. The reason why we're doing that is that if we already filtered the building height based on the confidence levels, we should also do that for the buildings, so that we don't actually keep those buildings for which we are anyways not going to even do the height, or for which we don't have the confidence that there are part of that. So what we're going to do here is using the field from this open building SF, which is called confidence. we're just going to filter it, and we're going to say everything that is equals to or greater than the confidence level. We want to keep that. We're almost ready to create our map, but before we do that, we need to assign a certain height to those polygons. And the best way to do that is to use zonal statistics, which is going to give us a number for every polygon based on a certain function that we choose. You can choose different functions. So what I'm going to choose in this one is I want to have the highest heights among these different pixel values for a certain building polygon. So first of all, for doing zonal statistics, we're going to use exactly extract R, which we previously loaded. It's super fast. And then what you need to do here is for the polygon layer, of course, or actually for the raster layer, for what you want to, for what we want to calculate height, we need to use this one, which is masked. And then we need to use Open Buildings SF, so that SF object over which we're going to calculate those values. And then here for the function, of course, you can use many functions. You can use average, so that would be mean, median, minimum, maximum. I'm going to go here for maximum, but you can also try out some others. Really depends on your use case. All right. And once you actually have this, you're going to get a data frame here. And the values here are going to be in the same order as the ones in this Open Buildings SF object. So what we need to do essentially is just put them together. So bind them together using this cbind. So column-wise binding. So we're going to put together this Open Buildings SF1, and we're going to put together this data frame. And the very last step, very important, is make sure that everything is still an SF object. So as we are preparing to create first our 2D map of building heights in this part of Mumbai, I would really like to think about the ways we can enrich it. And one of the ways to do that is to add roads to the map. The easiest way would be to add OpenStreetMap roads, as we did in one of the previous tutorials. So we're just going to follow the leads there and fetch the roads data for that city buffer that we previously defined. So first of all, we're going to use that bounding box that we have, and then we're going to call OSM data, which you previously installed. And then we're going to say that we want to fetch this data. Now, we don't need everything, of course, from the OSM data, because OSM data has a lot of things there. What we need to do is we need to tell here in this add OSM feature that we want a feature which is called highway. Highway is essentially a code name for roads in OpenStreetMap data. And then the last step that we want to take here is make sure that this OSM data is returned in the SF format. So for that, we just need to provide here this function, very convenient one, OSM data SF. Now, this is actually going to return you a lot of different, shapes or types of vector data for the roads. We just need lines. So essentially, we're going to create a new object, which is going to be called city roads. And then from these roads, we're just going to fetch an object called OSM lines. So these are the different types that you can fetch: points, lines, polygons, multi-lines, multi-polygons. So we're going to fetch OSM lines because those are the ones associated usually with roads. And then once we do that, what we're going to do is we're going to intersect this. So we're going to intersect with our circle object. I know we did get the data for this bounding box, but we essentially need for that buffer only. And once you do that, the best way to make your data in a smaller format and then easier also for plotting and later on rendering is to declare this from a line to be a multi-line string. And you can easily do that by simply passing this stcast, which comes actually from just SQL. And then here you want to say multi-line string and then convert everything into that. So that essentially when you plot these roads, you should be able to see roads like this for this specific extent, of course. All right, and we can finally now write a code that will prepare, lay the ground for our map, and then essentially create the map. What I like to do first is I want to define the theme for our map that we can then use later on. So I'm just going to call this one theme for the win, as I always do. And then over here, I'm going to define several things. First of all, I'm going to define a minimal theme. I like actually to use theme void, which gets rid of all the excess things around it. But since we're also going to use rayshader does not really deal well with it. So we're going to need to define some things here. And we're going to define within this theme option, which allows you to actually customize pretty well. So what we're going to do is we're going to first of all get rid of some of the things that we don't not going to show there. So one of them is, for example, those axis lines. That's one thing. The second thing, what we don't need is also the titles. So axis titles, both the one for the longitude, so the x axis, and also the one for the y-axis. Then we're also going to get rid of not just the titles, but also the text, which is also used for the coordinates, for the x coordinates and the y coordinates. So axis text x and axis text y, and element blank is ggplot2, for which we're creating this theme, is used to simply get rid of these, so not to show them. Then for our 2D plot, we are going to have a legend, so we're going to show it. And here we can define legend position. Now you probably noticed in those raster files, and also when I plotted them, but also when I plotted now our roads just a moment before, that there is some space in the lower left corner. So we're going to use that space and put the legend there. So that means that the x value of our legend needs to be low, and also means that y, so the height of it, so the next one, it's also need to be even lower. So both the so to say longitude and the latitude of our legends need to be low, so that it end up in the lower left corner. Of course, you can play with this one. This is going to definitely depend on your own buildings, how they're positioned. In my case, this is how they're positioned. Then there are some things that we do want to show, and they are also connected to the legend, and one of them is the legend text or legend title, so to say. So so for the legend title, we want to have here elements text, because essentially we're dealing here with text. And over here, then you can define things. For example, maybe we can go for 8 pixels. It would be good to have a color which is going to be light. For example, this light gray, because I do want to have a darker background, which I think is going to be more effective. And then I also need to actually place this legend maybe a bit lower here, so maybe -20. We also want to have legend text, so the same way we have legend title. So I'm just gonna go ahead here and paste so that I make it easier, and then instead of title, I'm just gonna put here text. So it's also an element text, but we want to also make it smaller here. And then we don't need this vertical adjustment, so we just want the color to be also light gray. Then there are some other things that we want to also get rid of, and one of them is the grids. So there are minor grids and the major grids. So we're going to start with the major one. We're also doing all this simply because we chose the minimal theme, and we need to then manually get rid of some of these things. One thing that we want to define is the plot background. So as I said before, I would like this to be dark. So I am going to go ahead and put this and define element rect here, because it's a rectangle. And then I'm going to go ahead and choose here the color. We can, for example, go for black color, or maybe later on when we define the palette, you can also choose the dark color of the palette. Essentially, I'm probably going to go for that option, which I can change later. But for now, let's just leave it here. Then we can go back to that one. And then the last option here that I would like to define in my theme are the margins. It's a very, very important one to get rid of that extra space around the plot that you don't essentially need. And to do that, you need to here just define the list of 4 sides for which you want to do that. We're going to decrease by 1 centimeter for each side. So starting with the top side, then moving to the right-hand side, bottom side, and then ending with the left-hand side. But in order for us to tell actually ggplot2 that we're dealing with centimeters, you also need to define them over here. Okay, so we define the theme that we're going to use, and the next thing is to define also the color palette that we're going to use. So the easiest way is simply to call the HCl colors, and then to choose one of them. You can also go and Google HCL colors. You'll see they have a very rich palette. And one of them that I want to use is Inferno palette because it has such vivid colors. And I'm going to take 6 actually from this one. Now, once I actually create this, and we can also inspect these different colors, what you should be able to see here is that we have here these colors. So it starts with very dark and it ends up with very light. What essentially I'm going to do is I'm going to take this first one and I'm going to use that also for the plot background. So I'm just going to go back here, and you remember in this plot background that I previously defined a theme, I'm just going to replace this one with actually calls and the first element of the calls, which is actually the, you know, that dark color. And then I'm just going to rerun this theme for the win, and that everything is fine there. So I'm just going to close it back, and then we go back to here where we define colors. Okay, now we have everything, and now we can create the code for our map, and then we can also save our map. And here we'll be working with ggplot2. So the one and only thing that we want to have here, well, not the only thing, one of the things, very important one, is the building height. So this is again SF object, so we need to provide here GMSF so that ggplot2 understands that we are passing the SF object. Then you simply need to pass this one. And it's very important that we want the polygons to be filled with a specific color based on the height, where those with lower height, they're going to be dark, and those with higher, they're going to be lighter. So we're going to say here that for filling height, we're going to use the height column that we previously created using zonal statistics. And then I don't want any borders of these buildings. So I'm simply just going to say here that the color, so the borders of the buildings are going to be not visible. And then I'm using actually here a bit newer version of ggplot2. So I have line width. If you're using the older, you might have size. So you should check that out. So I'm just going to set size to 0. So that would be the first one. The second one, we want to add also roads in our 2D map. So for that purpose, we need to also include this city roads, all right? And then one thing we want to, check here is how thick we want to have. Again, I'm using here line width. If you have an older version of ggplot2, please do use size. So I'm going to go for, let's say, 0.2. So that's going to be a very thin lines, but still quite visible. And let's say I would like those roads to be white color. So I want the white. All right. Now this is not all, because we do need to also define the colors for this height, and this is done through scale fill argument. The reason why I'm using scale fill and not scale color is that because my main aesthetics here is fill. So this thing needs to match. And one other thing that is important, because this is a continuous value, you cannot use here scale fill manual. It needs to be based on gradients. So we're doing here gradients, and I'm using this, for example, gradient. Now you can also define here legend because we have it. I don't know, I'm going to leave it empty. I know I defined the parameters for legend title, but I'm just going to leave it empty. And then what I'm going to use here is I'm going to define, first of all, colors. Colors is going to be that calls thing that we have. And then very importantly here, because we have NA values, and that would mean that a lot of plots then is not going to show anything. For these NA values, I'm again going to use this calls 1, so that dark value. Everything that is NA, it's going to be filled with that dark. All right? And then we can go ahead and customize a bit our legend, and that is always done using the guides argument. All right? Now, for the guides argument, it's important that you say what is your main aesthetic for which you're building this legend, and in our case, it's fill. And then because we want to have a legend, a gradient legend, so the one that accounts for the continuous values, we need to specify here guide color bar, and then within these brackets you then specify what you need. I want, for example, this legend to be horizontally positioned, and then I also want to define my bar heights and my bar width. So I can here define in terms of the units. So for example, I would like the height to be, let's say, 2 millimeters, so that would mean 0.2 centimeters, because we're dealing here with centimeters. That's the first thing. And then I want the same thing for the bar width, but I'm going to, of course, change because it's a horizontal one. I want it to be a bit longer. So let's say I want it to be 5 centimeters long. All right. So I put here, I leave this the same, but I just change here instead of a bar height, I just put bar width, and everything else is the same. Then there are some other things that you can define here. Of course, how do you want to position your labels? Let's say I want them to be below, so that's why I chose bottom. Then there is also this tile position. I would like tile position to be on the top, so to be above the legend keys. Then there is also an option, how I would like to do, let's say, legend title. I don't know actually why I defined the title position, because I'm not going to have it. You see here, I am omitting it, but this is just for you to see what else is there. One thing that we can also do is, for example, how do I want to position, let's say, my labels. So if I want it in the middle, I can, for example, put 0.5. And then what else I would like, perhaps one more thing that is very useful is I don't want to drop any of the missing categories, for example. So those are the things. Anyways, once you're done with this guides part, and it's quite a long one, to be honest, especially if you start really customizing your legend. Once you're done with that, what you can do is simply call this theme for the win. And then make sure that there are, of course, brackets here, so that means you can call it. And that's how you actually create this map. All right, so this is the 2D map, all building height for the specific part of Mumbai, where you can see actually several things. So you can see that there's a lot of high buildings that are clustered in this middle part, in this commercial district. And then as you go outside of that ring, that size actually decreases. You can also see here the roads that we added. There, of course, we cut those roads using the buffer, so that's why it doesn't cover essentially everything around this perimeter. So if you want to have actually more roads than this, you can simply maybe not intersect them, you can keep them. Now, before we render a 3D scene with buildings, what I would like to do is do two things. Two things. One thing is we're gonna first of all go back to that codes, the ggplot2 codes, and we're gonna actually comment out this one. So you just need to click on Windows Control and then slash, and then, or simply just remove this one. So we don't need the roads because we are gonna render the roads separately. That's one thing. And then over here, we're actually gonna get rid of the legend. Now, you don't need to do that. I'm just doing that because I want to have, this in a more, to look basically like a poster. I want it to look cool, so I'm gonna get rid of the legend, and that's why I'm adding this, the legend position equals none, and then I'm simply actually gonna run this, and then we can go back and write the code which is gonna help us render the scene. All right, this is not all, because I also want to show you how you can create some awesome 3D building height maps, and for that we will again call to rescue the awesome rayshader package. Now, in terms of rayshader, what we can do is utilize this ggplot object that we created. Isn't that awesome? So we can use plotgg function from rayshader, and then as a GG object, we can pass that map object we have. And based on this, we can build a render. So first of all, we need to provide in inches what is going to be the width and what is going to be the height of the map. So I'm going to put 7 inches each. Then you can also define a window size, but just be careful, because when you're defining window size, it requires you to define in pixels instead. So also make sure that if you are, of course, it's going to be different from the inches, but make sure that the ratio is the same. So if you put here 7 and 7, this should be also 6 and 6, right? Or 600 and 600. Then we will also here choose a background, and again we want the background to be dark, so it's going to be this the first color in our palette. Then here you can choose how actually tall the building is going to be. I'm just going to go for default here. So the scale is 150 by default. If you want the buildings to be even higher, you can use a higher number. If you want to lower them, you can use a lower than 150. Then I'm actually gonna turn off the solid plane below it. You can also turn it on, and then, for example, maybe you can take a circle because we already have a buffer. Perhaps it's going to have actually a nice look, but for now I'm just gonna turn it off. And then definitely we're going to have shadows because we want that 3D effect. But I'm actually going to set the shadow intensity for a bit lower one, which is 1. If you want shadow to be stronger, you need to take the value which is closer to 0. And then here we're also going to have this is going to be the degree of the scene. So I'm going to for now choose something like almost normal to the degree of the scene, and then we can actually change it later. This is how much it's going to be tilted around the axis, so it's not going to be tilted. And finally, this is zoom. So I'm going to choose some kind of a mid zoom because the highest zoom is 1 and the highest zoom out is 0. We got our first render scene. As you can see, it's almost like a 2D map, and that is because we chose the angle degree, which is almost close to the normal degree of 90 degrees. And of course, this one also doesn't have roads, which are going to add later on. But for now, what we're going to do is we're going to re-render the scene using a sharper degree angle so that we add a 3D perspective to this render scene. Okay, so to change the degree angle, we can simply go for rayshader and then render camera. And then for render camera, we can, as I said, choose like a sharper angle here, let's say 45 degrees. We can keep this theta value, so it's 0. Otherwise, you can also choose it. And I think we're going to bit zoom out so that we decrease also the size of the map. All right, this looks much better. We added now the 3D perspective to the scene, and we are now ready to also render the roads. All right, adding roads is not that difficult. Essentially, what we're going to do is use a dependency package from rayshader, which is called ray render. So this one has something which is called a render path. And render path is very easy if you have an SF object like we do. What you need to do is just use this let function or attribute, and then pass here the city roads which we previously created. All right, and then you also will need to provide an altitude here, but you can provide just like a constant altitude. Let's say we do a default 1, because we essentially are not going to have the base layer that much elevated except for the buildings. But the roads anyways are not going to go over buildings. They're going to go around. So altitude of 1 is totally fine. And then you also need to find or define the extent of the scene where these roads are going to be placed. And for that, we can just use our building height data, of course, again, in the SF format. Then the question is, okay, how much are these going to be elevated, these roads? We're not going to elevate them. We're going to simply like put the value of 1. And one of the last questions is how thick the lines are going to be. So I'm just going to go for 2. I think that in render path, the default one is 0.5. So I'm just going to make them a bit thicker. If it's too thick, then you can re-render again things. And I'm going to keep the road color again white as we did before. Okay, cool. So apart from the 3D perspective of buildings, now we also have the roads. And the roads are going exactly around the buildings and not over them. And this is why we didn't really include the roads in the ggplot and then render them, but edit them actually afterwards. And this took around 1.8 minutes. So something that you should also take into account, because a rendering roads in rayshader tends to be a bit slower than rendering the scene itself. Right, and the last step is of course to render the object itself and then save it as an image file. So let's start off by first of all defining the name of that file. So I'm just gonna use Mumbai Buildings and then append to it a 3D name. So it's gonna be like, for example, this. And then we can, of course, go to a rayshader and call its function, which is called render high quality, which is going to allow us then to, save this file. So speaking of which, for the file name, we're just going to pass here file underscore name. And then we're going to, of course, allow a rayshader to show us how to preview how the rendering process is going. For the lights of the base floor or the base layer, we're going to just turn it off. And then after that, what we're going to do is we're going to go for environment lights. So for the environment lights, we're going to go ahead and choose one of the environment lights which we used in previous tutorials, which is called Brown Photoshop Studio HDR. You can also check how you can download it. Don't worry, again, I'm going to provide actually this one in the description box below. And also in the final code, I'm going to provide the full code for actually downloading and embedding this one. Now, for demonstration purposes, I'm just going to show you here how is it called. But for the running, please consult the code that I will provide after this video in the GitHub repo. All right, so once you have this one, you also want to define how intense this is going to be, this environment light. So you can then use this intensity underscore n. And if one is, let's say, a default one, I want it to be a bit lighter. So I'm just going to go for 125. You can essentially also increase that one. And then one thing that I like to do as of recently is to also diffuse a bit of the color of the base layer. And for that purpose, what I'm going to do is I'm going to actually diffuse that dark color of the background, so that actually there are no like extra shades that would prevent us from seeing our core buildings. Because we are rendering also lines, it's very important that you define here line radius. And for the line radius, we're also going to go for the size of 2. Again, if this is like too big for you, you can decrease it. But if it's too small, you can also increase it. One of the things that I like to do is turn off the interactive modes in rayshader, because that might lead to crashing of your scene. So I'm just gonna, turn it off. And then I'm gonna allow a parallel processing. And then finally, you can also define what are going to be in pixels, of course. What is going to be the pixel size of your width and the height. And again, pay attention here. So this needs to be in the same ratio that you use to also render your scene. And now when you run this, you're ready to go and to render this scene. And this is our final map, the 3D building heights of that piece of Mumbai in its full glory. I'm really happy how this turned out. Let me know what you think in the comment section below. All right, guys, this is how you can fetch the data from Google Earth Engine for open buildings, and how you can create some awesome 2D and 3D building height maps using this data. Let me know in the comment section below how this went for you. And I'm also looking very much forward to your own projects and how you take this tutorial on a journey across the world. If you are new to R and you seek to expand your geospatial and data visualization knowledge in R, I prepared a few cool tutorials for you, so do check them out. See you next time.